好了，那么接下来呢，我们来看化油器结冰的实例。
As most pilots or shade tree mechanics will probably recognize, this is a carburetor and this is ice. And for pilots flying an airplane like this, one without fuel injection, when these two come together, the result can be very disturbing.
Carburetor racing can occur any time of the year, even on a hot day, but the most prevalent times are during cool summer and early fall days with high humidity or visible moisture in the form of haze or rain. The Venturi effect of air passing through the carburetor lowers the temperature considerably, causing water vapor to freeze and eventually, without correction, can cause the engine to quit. The first sign of carburetor icing may be a slight reduction in the RPM of the engine or a loss of manifold pressure. By applying carb heat, a flow of heated air from the exhaust melts the ice and eventually allows...
注意看啊，它刚才拔的这个应该是化油器加温。在我们飞行的时候呢，如果是飞这种比较老的飞机的话，一般来讲呢，应该是每过5分钟到10分钟的这样一个时间，就要把这个化油器加温呢打开一下，工作个大概10秒到20秒的时间，再把它关掉。这样的话呢，就时刻的防止化油器那个地方发生结冰现象。
Full power to return. It may be necessary to adjust the mixture to smooth out the engine, so consult your flight instructor for proper usage. If you do have carburetor ice, be prepared for a further loss of power when carb heat is initially applied, as water from the melting ice is drawn into the engine. Be patient and allow the ice to melt. Power will be restored in a minute or so.
If the carb heat is turned off before the ice is completely melted, the engine may fail entirely. And with a cold exhaust, you won't have enough hot air to melt the ice and restore the power.
A check of a pilot's operating handbook will list the recommended time to apply carburetor heat for your particular aircraft. Anticipate and check for carburetor icing by applying carb heat periodically as an anti-icer rather than a de-icer. And finally, be aware that the use of motor vehicle gasoline or MOGAS can dramatically increase the temperature range for the occurrence of carburetor icing.
Carburetor ice can be fatal, but learning to recognize the signs of carb ice and knowing the steps to take to prevent it can work towards making every a safe and enjoyable one.
All right, so the above is about the BIOS freezing issue, which essentially, as we mentioned earlier, is actually a combined relationship between the effort law we discussed and the complete memory state equation mentioned in the previous lecture. Regarding the effort law, due to reaching the initial position recently, the acceleration causes a pressure drop at the throat. Then, since we say that a freely flowing fluid, like freely flowing air, is approximately an incompressible fluid, we can assume its density remains constant. At this point, due to the pressure drop, it results in a change in its temperature. From the ideal fluid, or an ideal gas state equation, we know its temperature will drop. So, what happens when the temperature drops? It causes the local temperature to fall below the dew point, leading to the moisture in the air being extracted, and eventually causing icing at the carburetor's throat. Therefore, we need to use carburetor heating to prevent icing from occurring. So, what happens is the chemical icing issue mentioned above. After discussing chemical icing, we will further advance our discussion to the flight problems of the aircraft. Next, let's take a look at the banana ball and the Magnus effect. What is the Magnus effect? In 1997, Brazilian football star Roberto Carlos demonstrated an impressive free kick during the Four Nations tournament where the football curved beautifully in the air, bypassing the crowd. Because the trajectory of the ball resembles an intersecting shape, such balls are vividly called banana shots. So the question arises, how does such an impressive banana shot achieve a sharp curve? The secret behind this is the Magnus effect. At the moment the athlete kicks the ball, friction causes the ball to start spinning. As the soccer ball moves forward and spins in the air, the airflow around it also begins to rotate. On one side of the soccer ball, the direction of the generated airflow is the same as the relative airflow direction during flight, which accelerates the airspeed in that area. On the other side of the soccer ball, the directions of the two airflows are opposites, which reduces the airspeed. According to Bernoulli's principle, areas with higher flow speed have lower pressure, and areas with lower flow speed have higher pressure, thus creating a pressure difference on the two sides of the soccer ball. This gives the ball a lateral force, allowing it to curve. Of course, this technique is not only seen on the soccer field, it can also be observed in many other ball sports such as table tennis, tennis, billiards, and baseball. However, the distance on the field is ultimately limited. To truly appreciate the dramatic effect of the Magnus effect, a foreign experimenter directly threw a spinning basketball off a 100-meter high dam. After releasing it, they found that the basketball did not fall straight down, but instead glided gently along a curved path towards the distant lake surface, as if on a slide. In summary, the Magnus effect can easily alter the trajectory of spinning objects in the air. So, can it be used on airplanes or ships? The answer is yes. As early as the 1980s, there were ships that utilized this ancient method of navigation. When a crosswind blows, the rotating cylinder can generate forward thrust. Similarly, many aviation enthusiasts create simple cylindrical flying devices that do not require wings and rely solely on the rotating source to provide lift. In the military field, the Magnus effect also has a significant impact on the aerodynamic performance analysis and guidance control of spinning projectiles and missiles. Alright, so next we have observed the Magnus effect generated on a rotating cylinder or a rotating sphere. Under the influence of the Magnus effect, essentially, it is the area where the flow speed is faster. Pressure is lower, pressure is lower. For example, in slower areas, the pressure is higher. These two parts create a pressure difference, thereby generating a direct aerodynamic force. So, if we were to directly illustrate the Magnus effect, it can be represented like this. For a cylinder, let's assume, if it were a non-rotating bead, then when a flow hits the front of the cylinder and then flows past it, I ask everyone, what should the flow pattern be like on the top and bottom parts? There should definitely be some variation, right? So is there any relationship between the top and bottom? The top and bottom should be symmetrical, shouldn't they? Isn't that right? Because it doesn't rotate, right? So it should be a vertically symmetrical flow. At this point, if I add a rotation to this cylinder, essentially it's equivalent to superimposing a rotational flow on this flow. This rotational flow should actually have a higher rotational speed. The closer it is to the center, and relatively speaking, the rotational speed will be smaller the further out it is. Because for a rotating cylinder like this, the part closest to it will definitely rotate the fastest, right? Very far away, it certainly has no effect. So, it's a process where the rotation is smaller on the outside. Many times we can equate such a flow field to a combination of a non-rotating cylinder and a rotating cylinder, resulting in a rotating cylinder without speed, without forward velocity, to obtain this flow field. At this point, we will observe such a phenomenon, which is a flow from left to right, passing through a continuously clockwise rotating cylinder, resulting in this final combined flow field. So, will this combined flow field still be symmetrical from top to bottom? At this point, it won't be symmetrical, right? So what about the upper surface? Due to the rotation, the flow velocity direction combines with the direction of the free stream, resulting in a faster speed in this area, correct? what characteristics do we observe from the streamlines? The streamlines are denser, right? So, with the increase in flow speed, what about the pressure? It decreases. Whereas on the lower surface, the direction of rotation and the flow direction are opposite, correct? From the streamlines, we can observe the distance between them. It increases, doesn't it? In this case, the flow speed decreases. And the pressure increases. So the pressure is higher below and lower above. At this point, an upward force is generated, which is essentially lift. This method of explaining the issue is actually the circulation of lift. Is this explanation method acceptable? What does circulation refer to? It refers to this concept, right? If there is circulation flow that is superimposed on an incoming flow, then this will result in the generation of lift. In addition, and regarding this, let's first take a look at this demonstration. Initially, when it is not rotating, it is a symmetrical flow, right? Once it starts rotating, we can see what happens above. The smoke streamlines converge, correct? The distance between the smoke streamlines below widens, so the pressure below is greater and the pressure above is less, resulting in the generation of lift. At the same time, when it is rotating, we can actually observe another phenomenon. What is this phenomenon? We notice that after it starts rotating, the flow in the front part. There will be an upward change, right? And the flow at the back. There will be a downward change. So what about this flow? In the front part, originally it was moving from front to back. But when an upward movement occurs, we call this area the upward airflow. And after flowing past this rotating cylinder, the air moves upward and then turns downward. This area, we call it the downward airflow. So when the direction of the airflow changes, what inevitably happens? It means that the momentum of the air has changed. So how do we cause a change in momentum? There must be a force acting, right? So this part of the force is actually the lift generated on this cylinder, which means, so the air was originally moving upwards, and then it changed to moving downwards. This means that the cylinder exerted a downward force on the air, causing the direction of airflow to change. Consequently, the air exerted a reaction force on the cylinder, creating an upward force. This way of explaining is considering the principle of lift generation from the perspective of momentum. These are two very important methods of explanation. All right, above, we discussed the application of Bernoulli's principle from three different perspectives. Next, we will introduce the most important part of this lecture, which is about the application of Bernoulli's principle in airspeed measurement. Some related knowledge. Here we also touch upon an important system of the aircraft, which is the static pressure system. Are our students familiar with this system? Yes. At our SOFA campus, we actually have such an aircraft, right? This is a domestically produced J-8I fighter jet. Now, let's focus on observing this particular component of the aircraft. This component is actually the pitot tube of our aircraft, which is a device used to directly measure the speed of the aircraft relative to the air. By applying Bernoulli's principle, which we learned today, we can analyze its working principle. Let's first take a look at the structure of the pitot tube. This tube is actually a double-layered sleeve. We notice that first it has a blue tube in the middle. What about this tube? At the very front, there is an opening, which we call the total pressure hole. Then, after passing through this total pressure hole,
the flow will continue upwards and out in a short time, reaching the device at the back. Additionally, outside of this total pressure hole and the tube, there is another layer of foam tube. Note that this foam tube does not have an opening at the front. Its opening is actually on the tube. There will be 2 holes, or even more, on the side wall. These holes are what we call static pressure ports. After passing through the static pressure ports, the tube remains sealed until it reaches the end of the control tube. Finally, it will also vent out through another tube. So when the airplane reaches a state of equilibrium during flight, what actually happens? The total pressure port will not allow air to enter. Instead, it will eventually output a pressure outward. Similarly, the static pressure port will output into the static pressure tube, and correspondingly, there will be a pressure output. Let's take a look at how it specifically works. It works like this. Let's assume that we take the empty airplane as our frame of reference. We assume the airplane is stationary, and the air is blowing from afar towards the airplane. This way, it is more convenient for us to analyze. Next, we want to focus on analyzing the airflow conditions at 3 key plane positions. First, the first position is the plane at infinity. We say that at this point, because it is very far away, the flow field around the airplane cannot affect such a plane. And now we assume the airplane is stationary and the air is blowing towards it. So, I ask everyone at the distant front plane 1, what should the speed be like at this time? It should be the relative speed between the airplane and the air, right? And what about its pressure? It should be the atmospheric pressure of still air, right? So, this is the situation at infinity, where the section is not affected by disturbances. Its speed is the relative speed between the air and the airplane, and its pressure is the undisturbed free stream, atmospheric pressure. All right, so when this air continues to push forward, what happens as it approaches the airplane? Eventually, it collides with the total pressure port at the front end of the countless chestnuts at plane 2. When it reaches a stable state, the pressure inside will be completely equal to the pressure outside. Now, at this moment, when it hits the very front end, at the point of the total pressure port, what do we say about its speed and pressure at this point? We say that at the very center, when it hits here. First, we discuss what happens to its speed. After completing this, we talk about reaching a stable state inside here. No more air will be coming in. So, in this case, what should the speed be at this point? Its speed will decrease to 0, right? So, when the speed decreases to 0, what is the pressure at this point? At this moment, the pressure becomes the total pressure, correct? All right. And then, very quickly, the airplane, due to the narrow air ring, will rapidly accelerate after the airflow passes around the pitot tube, for example. Because the pitot tube is very narrow, the disturbance to the flow field is very limited. So after flowing a short distance, what happens? In fact, its speed will quickly return to the speed of the flow far ahead. And when it reaches position 0.3, its speed will once again return to the speed at plane 1. Now, let me ask you at this moment, what should the pressure be at the static pressure hole at this time? The atmospheric theorem is this. What should the pressure be? Since the speed has become the same, right? The speeds at these 2 sections are the same. Therefore, the air pressure should also become the same. Correct? Yeah, but so at plane 3, the atmospheric pressure returns to the atmospheric pressure far ahead. At this point, we can use the kinetic energy theorem we mentioned earlier. Here we say, at this point, which pressure is it? Total pressure. Total pressure, right? Yes, that's it here. And then, what pressure is at this position?
It's static pressure, right? So if we subtract the two pressures, we can obtain the dynamic pressure. We process this dynamic pressure because it contains the attack speed term. Therefore, we can determine our attack speed here. Pay attention to a term where we say this dynamic pressure and total pressure are obtained. Right. Obtained on plane 2, right? And then this corresponding one, actually this tube, we call it a Prt1 tube. Sometimes it's referred to as a Prt1 tube. Therefore, regarding total pressure, sometimes it is also referred to as Prt1 pressure, using the term people's pressure. In fact, it corresponds to total pressure, because some Prt1 tubes actually do not have static pressure holes. We will explain this in detail later. Alright, so here we say that after obtaining the static pressure and total pressure through the Prt1 tube, we need to use a certain method to derive the aircraft's airspeed from the dynamic pressure. What do we do? So here, let's take a look. Let's take a look at us. After passing through the Prt1 tube, we will need to connect the total pressure and static pressure pipes to our airspeed indicator. The structure of the airspeed indicator is actually somewhat similar to the altimeter we discussed in the previous lecture. It also consists of an airtight casing with a sealed diaphragm structure, as long as the air pressure inside the casing differs from that inside the diaphragm. The diaphragm will correspondingly expand or contract. This expansion and contraction of the diaphragm are used to drive the corresponding mechanical pointer to rotate. In this way, the airspeed of the aircraft can ultimately be displayed on the gauge. So, this is the principle of the aircraft's airspeed indicator. How exactly do we determine this airspeed? As we mentioned earlier, we have the total pressure and the static pressure. And by subtracting the two, we can obtain the dynamic pressure. Right. Once we have the dynamic pressure, we simply multiply it by 2, then divide by the density and take the square root to get the airspeed. Right? However, during actual flight, we encounter another issue. Do you know the density around you when you're flying in the air? It's very difficult for us to measure our density, right? Therefore, in the logic that operates within the airspeed indicator, what density is used? It uses the density under standard atmospheric conditions at sea level. What is this density? It should be 1.25 kilograms per cubic meter. So we can see the speed obtained at this time. In fact, in many cases, it is not an accurate speed, right? It actually only reflects a relative pressure relationship, correct? However, because directly telling you the pressure from a dimensional perspective might be uncomfortable, we use a speed to represent it. The speed obtained is what we refer to as the indicated airspeed of the aircraft, represented as IAS, indicated airspeed. Alright, so under what circumstances will the indicated airspeed be equal to the aircraft's true airspeed? Intuitively, we say that only when the air density around you is equal to 1.25 kilograms per cubic meter, the airspeed indicated by the airspeed indicator is the true airspeed. But more often, it is actually just a relative value, but this relative value in terms of safe flight is actually not sufficient. Additionally, what is another important concept? True airspeed refers to the relative speed between our aircraft and the air. So, in windy weather, is the aircraft's speed relative to the ground. The true airspeed, 10th, 7th, 3rd, 4th, 4th, 4th. In fact, in most windy weather conditions, the speed of the aircraft should be relative to the ground speed, which should be the airspeed, combined with the ground speed. the vector sum of the airspeed, and wind speed is the speed relative to the ground. Later, we will provide a detailed introduction to this. All right? Let's focus on our wind speed indicator. Now, let's take a look at the composition of the entire system. The pitot-static system is connected to the airplane's altimeter, airspeed indicator, and the vertical speed indicator. These instruments inform the pilot of their altitude, speed, and rate of climb or descent. These are determined by measuring the atmospheric pressure. The pitot-static system gathers pressure information from two sources, the pitot tube and the static ports. Hence the name. Pitot-static. The pitot tube is designed to measure the pressure of the air as the airplane flies through it. In smaller aircraft, this tube is located under the wing so it can measure the airflow without any interference. Sometimes, aircraft manufacturers will use a pitot mast instead of a tube shape, but it still functions in exactly the same way. On the backside of the tube, there is a drain hole, which allows any rain or water that collects to drain out and not enter the system. Finally, the pitot tube can also be heated. This is used to prevent ice from forming on the tube, which could potentially block the hole and cause a malfunction. Functionally, the counterpart of the pitot tube is the static port. The location of this port will vary with different aircraft designs, and it should be positioned where it can measure the static pressure of the air, unaffected by the dynamic airflow around the airplane. On the Cessna 172, the static port is located on the left side of the forward fuselage. The pitot tube and static port openings are connected to tubes that join into the pitot-static instruments. The pressure inside the instruments matches the pressure of the outside atmosphere. All three pitot-static instruments connect to the static ports, but only the airspeed indicator connects to the pitot tube. Sounds simple, right? Okay, the above is the aircraft's pitot-static system. Let's take a closer look at it. Its schematic diagram is roughly like this. As for the vertical speed indicator and altimeter, which we discussed in the previous lecture, the pressure needed for them to work is actually the static pressure from the free airstream ahead. This is what we refer to as the static system. The static pressure in this context refers to the static pressure of the free airstream that has not been disturbed by the aircraft. This is a very accurate way of expressing it. Of course, in some instances, it is simply referred to as static pressure for brevity. This static pressure, as mentioned in the Bernoulli's principle we just discussed, is actually just a very special case, right? So we say that both the altimeter and the airspeed indicator need to obtain the static pressure from the undisturbed free airstream. And then, for the airspeed indicator, what pressure do we need? First, we need a pressure from the front end. Total pressure, right? And then, what else do we need? The static pressure of the undisturbed free airstream. For most small aircraft, this static pressure is obtained through the static port or static plate, located on the side of the aircraft's fuselage. We encountered this in the previous session, and the placement of this is quite particular. It should be said that it is similar to the position of the static port on the side wall of a relatively long airspeed board. This ensures that when our aircraft is in normal flight and the airflow reaches this static pressure area, the speed at this point is approximately the same as the speed far ahead. In this way, the static pressure value it reads is the same as the static pressure value of the undisturbed free airstream far ahead. Additionally, there is a consideration for special situations. Sometimes the static port might become blocked or malfunction due to external impacts or other reasons. In such cases, we also have a backup static pressure source, which is usually located inside the cabin. This backup static pressure source can provide an approximate static pressure value to drive your altimeter, vertical speed indicator, and control instruments to function properly. However, the value it provides will not be as accurate as the one measured by the static port outside the aircraft, and there will be some error. This describes the general situation of the total static pressure system. For a small aircraft, let's note the main differences compared to the pitot-static system we discussed earlier. The source of its static pressure is not on the side wall of the pitot tube, but rather placed on the fuselage. The advantage of this is that the pitot tube can be made relatively small, so when flying, most aircraft usually need to pay attention to a pressure relief port or pressure relief plate on the side of the fuselage. As for large aircraft, let's see how it works. Here, we use the C919 aircraft as an example. This is during the test flight process, so the C919 is equipped with slightly more sensors. So, first, pay attention here. This here is actually the aircraft's static pressure sensor, or what we call the static pressure plate. It has many openings on it, which are used to measure the static pressure. Having multiple openings can actually serve as a backup safety feature. Then notice that it also has a pitot tube. Oh. Now, this pitot tube, note that it only measures total pressure, and so we also call it a total pressure sensor. It's the same as the one on the small aircraft mentioned earlier. It only has one opening at the front, which is used to measure total pressure. Then, this aircraft is quite special. During the test flight process, it also has a total and static pressure sensor, which simultaneously measures total pressure and static pressure. We can see that it has openings on the side, right? So it can also be used to read static pressure. So this is a common arrangement for the total pressure sensor on large aircraft. For regular commercial aircraft, they usually don't have this. Typically, there might be several sets of static pressure sensors and total pressure sensors arranged on the side of the fuselage. So, after we use these sensors to measure and obtain the pressure, we might still face some issues. The values we read might have some discrepancies compared to the actual values. Let's discuss what factors might cause discrepancies between the airspeed readings and the actual values. The first possible situation is what's known as instrument error. What is instrument error? It refers to the scenario where the total and static pressures you read are accurate, but due to your instrument, defects in the manufacturing process, or variations in quality, might cause the indicated readings to have slight errors. We refer to this as instrument error. However, for most modern aircraft, since our industry is very advanced, most instruments can minimize this type of error to a very small degree. Therefore, for most aircraft today, we can basically ignore the impact caused by instrument error. In addition to instrument error, there is another very common error known as position pressure error. Earlier, we mentioned that to measure static pressure and total pressure, we need to extend a pitot tube forward, right? Then we obtain the total pressure at the tip and the static pressure on the side. This is an ideal situation, but in reality, what might happen is that our aircraft could be maneuvering, right? During maneuvers, ideally, the pitot tube should be pointing straight ahead, correct? When your aircraft tilts up. At this point, the frontmost opening might not be perfectly aligned right. The pressure it receives could differ from the total pressure, and similarly, the static pressure obtained on the side might also differ more or less from the free stream static pressure. Additionally, for example, the pressure relief plate arranged on the side of the fuselage, in reality, on the aircraft. When maneuvering, the pressure it measures can also differ from the free stream flow. The impact caused by these differences is what we call position error and pressure error. Essentially, this is due to the measurement location not being ideal, leading to errors in the pressure measurement values. So we refer to it as position error or pressure error. This is the second type of error. Additionally, there is another situation that might cause the error we read, known as compressibility error. What do people say this lunch is? Earlier, we mentioned the principle we use to measure this empty stomach.
What is it? Throughout this lecture, what principle have we been discussing? Bernoulli's principle, right? Earlier, we emphasized that Bernoulli's principle has a condition for applicability. What kind of flow? If you have an incompressible flow, right? When the speed of the airplane is very fast, when it has already exceeded the low speed range of incompressible flow, then using the same method to calculate work will definitely be inaccurate, right? This inaccuracy is mainly due to an error brought about by the compressibility of air. Therefore, we call it compressibility error. Specifically, when the speed is relatively high, the airspeed value obtained is actually greater than the true corresponding value. This can have a certain impact on our interpretation. Due to these different errors, many times we need to consider whether these errors exist to assess the airspeed we obtain. Let's categorize them and take a closer look. First, the type of airspeed we mentioned earlier. It's called indicated airspeed. Indicated airspeed refers to the airspeed we directly read from the aircraft's airspeed indicator. The errors that indicated airspeed might include are in fact one being instrument error, although this instrument error has now been significantly reduced. Another one is, what other error? Right, position and pressure error, correct. So, if the measurement position is not ideal, what result does this cause? If we want to correct this, after adjusting for the position and pressure errors, we obtain this airspeed. At this point, we refer to this airspeed as calibrated airspeed. In the pilot's manual, there is usually a table that provides the relationship between indicated airspeed and calibrated airspeed. This is mainly used to correct the position and pressure errors we mentioned earlier. Once we have the calibrated airspeed, we also need to consider another situation. What other errors might there be? Compressibility error, right? Therefore, based on the calibrated airspeed, if we apply a correction using the formula for adiabatic compressible flow to the airspeed, the corrected airspeed we obtain is called equivalent airspeed. So, this is the process of step-by-step correction from indicated airspeed. Starting from the indicated airspeed, we correct for position and pressure errors to obtain the calibrated airspeed. Based on the calibrated airspeed, we then correct for compressibility effects, ultimately obtaining the equivalent airspeed. There is a very important commonality among these three types of airspeed. They essentially all reflect dynamic pressure. Why is that? Because when calculating this speed, it actually uses a constant density, which is the sea level density, of 1.25 kilograms per cubic meter under ideal atmospheric and standard atmospheric conditions. So, what do we do when we need to know the true speed of the aircraft relative to the air? We should first calculate the dynamic pressure using our airspeed, then use this dynamic pressure divided by the actual atmospheric density to obtain the final airspeed, which we call the true airspeed. So how do we obtain the true airspeed? Generally, we measure the temperature to estimate the local atmospheric density, and then use that density to convert the dynamic pressure to get the true airspeed. This true airspeed is mainly used in our navigation process. These are the four types of airspeed we commonly use. We need to understand how each one is derived. The indicated airspeed is read directly. By correcting for position and pressure errors, we obtain the calibrated airspeed. By correcting for compressibility errors on the calibrated airspeed, we get the equivalent airspeed. On the basis of the equivalent airspeed, we replace the fixed value of 1.225 with the actual density, the actual local air density. From this, we can obtain the true airspeed of the aircraft. Additionally, regarding airspeed measurement, we often encounter an issue when the pitot-static system malfunctions, affecting our data readings. Here, we present a thought-provoking question.
In an aircraft's airspeed and altitude measurement system, if the static pressure source becomes blocked, what happens? Assuming the aircraft is in a descent, at this time, what impact would this have on the readings? During actual flight, what phenomena might occur, and what possibilities could lead to the blockage of the static pressure source? There are also other aspects of local categories. Either it hit something, right? It could be an insect or a bird, or there could be icing conditions. As for blockage, we usually assume, to simplify, that it's crystallization. If the icing causes a blockage, then at this point, wouldn't it affect the entire pipeline between the inside and the outside? Completely isolated, right? What? Now, suppose the plane is in a descent process, and at a certain altitude, it suddenly gets blocked, then continues to descend. Yeah. What happens to the pressure? What is the relationship between the static pressure inside the pipeline and the actual external static pressure? Today we are going to have a small lecture. The static pressure inside the pipe should be less than the external pressure, right? Because the lower the altitude. The static pressure of the free stream should be greater, right? In high school, it was already blocked, and it no longer changes with your altitude. Therefore, during the descent process, its static pressure should remain unchanged, right? And what about the total pressure? Did it freeze? No. So what is the value of the total pressure? What will happen to the total pressure? During the descent process, how should it compare to the real value? It should maintain the same relationship with the real value, right? We didn't say we are accelerating or decelerating, right? So we are comparing it to the real value. All right, we have it. The comparison relationship between the static pressure real value and our measured value. We also have the relationship between the total pressure real value and this measured value. So, students, please focus on determining which one to choose. Both readings will be greater than the real value. Option B is that the airspeed indicator reading will be greater, while the altimeter reading will be smaller. Then, both readings will be smaller. In this case, the anemometer reading will be smaller, while the altimeter reading will be larger. So, students, take 2 minutes to think about this issue. We have already analyzed this process together, right? I think we can take another 2 minutes to discuss it together. By combining the working principles of the aneroid barometer and the altimeter, we can determine what it should actually be. You can ask about this question, or maybe it's still about high heels. This CPU thing, and is there anything else that should be addressed, right? Okay. You also need to have a bowl of beef soup. Holy restaurant, holy restaurant, holy restaurant. I will provide everyone with some very important information. I will provide everyone with some very important information. I will provide everyone with some very important information. I will provide everyone with some very important information. I will provide everyone with some very important information. I will provide everyone with some very important information. I will provide everyone with some very important information. I will provide everyone with some very important information. Please, 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 please. You press this video. We also have many people. We 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 have many people. Time's up.
So for this question, most of our classmates chose correctly. Yeah. It should be A, right? Aye. Let's see how to analyze this problem. Earlier we already mentioned, we have already discussed with everyone the process of the 5 colors, which actually is remain unchanged, right? As we change, as our position or speed changes, this reading, it no longer changes. All right. So, at this point, our plane is in a descending process. We just mentioned that in lower areas, the pressure is high, and in higher areas, the pressure is low. So during the descent, if it remains unobstructed, it should be the same as reality. It should be a process where the static pressure continuously increases, right? Or we could say it's the reading of our static pressure, or the static pressure reading we obtain from the free stream. It should be a gradually increasing process, but due to the blockage, it doesn't change. So, we find that the static pressure should be smaller than the actual value, right? Then we can say, once we have the static pressure value, we can actually use it directly to discuss the issue we mentioned earlier. This height issue, right? Since our current static pressure is smaller than the actual value, isn't it? The static pressure is lower at higher altitudes. So, the reading given by the anemometer should correspond to a higher reading, right? Therefore, it should be greater than the actual value, which should be the easiest to analyze. And as for the airspeed indicator, the airspeed indicator requires both the total pressure and static pressure values, right? For the airspeed indicator, our total pressure line is not blocked. So, the total pressure remains the same as the actual value. Just like here, we can apply the dynamic pressure equation we discussed earlier. The total pressure is indeed the actual value, but the static pressure is lower, right? So, what happens to the dynamic pressure? The dynamic pressure, when reduced, should be greater than the actual value. Therefore, the airspeed we read will be higher than the actual value. All right, this is the method we use to analyze such problems. And it's important for students to grasp it. After class, students can also consider what the reading of the vertical speed indicator would be in this situation. Please come back and think about it again. All right, let me review the main content of this lecture. We discussed the derivation of Bernoulli's principle. The purpose of explaining the derivation process is to help students understand its basic assumptions and the scientific steps involved in each stage. We hope that with some guidance, everyone can grasp this derivation process. Secondly, we talked about the application of the principle of conservation of momentum. What we hope everyone can grasp is the theoretical application, what it is and how we use it, how to utilize the conservation laws to analyze flowcharts. This content will be involved in much of the knowledge we will cover later. Then, in engineering, we have 3 applications. The first one we mentioned is the Venturi effect. The second one, what did we talk about? It's related to our flight safety. Carburetor icing, right? How does a carburetor ice up? The third application is directly related to our future studies, which is used to explain the principles of the origin of life. Then, in the last part of this lecture, we discussed the application of the conservation laws in our public measurement systems. What is the principle of the entire system?